Hello, this is Stat134, Lecture 14. On Wednesday, you have Quiz 3 covering Section 2.5, 3.1, 3.2, and 3.3. Last time we covered Section 3.3, where we talked about the variance of the sum of two independent random variables. And we also talked about the central limit theorem, which is about the sum of n independent and identically distributed random variables. And it is approximately normal for large n. Today we're going to give an example of the central limit theorem and also move on to section 3.6. We'll do 3.4 next time. And we're going to look at calculating the variance for a sum of dependent indicators. So, but first something about CLT. So imagine that you have 10 Poisson 1s. Okay, so the graph of Poisson 1 is shown in this picture here, and so it is very much not normal. But when you sum them together, you get a Poisson 10, and that is approximately normal. So that is the CLT at work here. We want to find the probability that S is greater than or equal to 15, and we're going to use this normal approximation, and we just need to know that the expectation, if X is Poisson mu, that the expectation and variance are both mu. So the variance of Poisson 10 is 10, for example. So great. So here we have X is Poisson 1, so the expectation of X is 1 and the SD of X is 1. So the expectation of S10 is 10 and the SD of S10 is square root of 10 times 1 or square root of 10. And that is just from the central limit theorem. And S10 is approximately normal when 10, 10. So the probability that S10 is greater than or equal to 15 is the sum of all those rectangles to the right of 15. If we want to do a normal approximation, we need a continuity correction starting at 14.5 because the width of the first rectangle is 1. And so we get 1 minus phi, 14.5 minus the mean over the SD, which turns out to be 0.077. Now, let's move on to the variance of a sum of independent indicators and start off with the variance of just an indicator itself. So variance, remember, is expectation of I squared minus the expectation of I quantity squared. And the expectation of I squared is P. And the expectation of I is P. So the variance of I is P minus P squared, or P times 1 minus P. Now, if X is binomial, we write X as a sum of n independent Bernoulli P trials, and the expectation and variance distribute across those sums. So we just get the expectation of X is NP, and the variance of X is NP 1 minus P, or NPQ. Now, on to section 3.6. Take a look at the reading guide for what to read in this section, but we're going to talk about the variance of a sum of dependent indicators. So imagine that you have a building with 10 floors above the basement. If 12 people get into an elevator at the basement and each chooses a floor at random to get out independently of the others, how many floors do you expect the elevator to make a stop to let out one or more of these 12 people? So you can just imagine at the ground floor, you have everyone getting on and pushing buttons. And the question is, let X be the number of buttons pressed at the ground floor. What's the expectation of X? What's the variance of X? So X takes values 1 to 10. And X we can write as a sum of 10 indicators. These indicators are dependent because imagine that no one pushes the first 9 buttons, then you can be sure that with 100% probability that that the 10th button will be pushed. So these indicators are dependent on one another. We'll define I1 to be 1 if the first button is pressed, 0 otherwise. So that has probability, the probability that the first button is pressed at least once is 1 minus the probability that the first button is not pressed at all, which is 1 minus 9/10 to the 12th power. So expectation of x is 10 times P1. Now the variance of x is the expectation of x squared minus expectation of x quantity squared. X squared is I1 up to I10 squared, and you can represent that product. It's going to be a sum of 100 terms, right? So you'll get I1 squared plus I1 times I2 plus I1 times I3 all the way to I10 times I10, right? And the expectation is going to distribute across those. So you're going to get the expectation of, sorry for the notation, but the expectation of I sub j as ij runs from 1 to 10. So that's 100 terms. One way to sort of visualize these products of indicators is just using a grid. So I'll have I1 to I10 on the top and on the side, and just look at the pairs that we get. We get the diagonals are I11, I2, I2, and so on. And the off diagonals are like I1, I2, and so on. So let's take a look at what I1, I2 is as a product, right? Well, I1 is 1 if the first button is pressed. I2 is 1 if the second button is pressed. So the only way that I1, I2 can be 1 is if both I1 and I2 are 1. In other words, if the first and second button are pressed. Otherwise, it's going to be 0. So we need to find this probability that the first and second button are pressed. You want to use a complement here because, for example, the first button might be pressed 5 times and the second button might be pressed 7 times, or the first button might be pressed 2 times and the second button might be pressed 3 times. There's so many different combinations there. It's better just to look at the complement, which is that the first button is not pressed or the second button is not pressed. So P12 is 1 minus the probability of that, and we use the addition rule here. So the probability that the first button is not pressed is the unconditional probability 9/10 to the 12th power. The probability that the second is not pressed is 9/10 to the 12th power, and the probability that the first and the second is not pressed is 8/10 to the 12th power. So we get P12 is 1 minus that. So now, so I1, I2 is the same as let's call it I12. It's an indicator. It's 1 if the first and second button are pressed. And I1 times I1 is 1 if the first button is pressed and the first button is pressed. In other words, the first button is pressed. So it's just the same as I1. So in this grid here, we have 10 diagonal terms and we have 90 off diagonal terms. And notice that the expectation of all the diagonal terms are the same. They're just P1. And the expectation of all the off diagonal terms are all the same. They're just P1, 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 2, sorry. So we can write the expectation of x squared is 10 times P1 plus 10 times 9, or 90, P1, 2. And of course, the expectation of x quantity squared is 10 times P1 squared. So the variance of x is 10 P1 plus 10 times 9 P12 minus 10 P1 squared. So when you're doing these types of problems, you just need to compute 2 probabilities. One is P1 and the other one is P12, right? So it all boils down to that. And the number of off diagonals that you get is the number of indicators that we have, which is 10 times 1 less than the number of indicators you have, which is 9. So if you have n indicators, it's n times n minus 1. Or in this case, n is 10, so we have 10 times 9. Yep. So then we are going to do a concept test, but to warm up to that, let's recall the multinomial distribution. If you roll a die 10 times, the probability that you get 2 1s and 3 2s is 10 choose 2, 3, 5. So 5 here is referring to other, not 1, not 2, but the other possibilities like 3s, 4s, 5s, and 6s. So we get 10 choose 2, 3, 5 times the probability of getting 2 1s times the probability of getting 3 2s times the probability of getting 5 others. So that's 1 6 squared, 1 6 cubed, 4 6 to the 5th. So then we did a concept test. A fair die is rolled 14 times. Let x be the number of faces that appear exactly twice. Which of the following expressions appear in the calculation of the variance of x? So again, there are two main terms that appear in the variance of x. Let's just go back to the example from before. There's P1 and P12. In this case, I've given you B here is going to be P1, and A here is going to be N times N minus 1 P12. But as it turns out, the 14 times 13 is the problem with A here because the number of indicators that we have is just 6. So it really should be 6 times 5 times P12. Now, let's just sort of go through this here. So I1 here is 1 if the first face appears twice, and I12 is 1 if the first and the second face appear twice. So those have the probabilities shown here, and it's worth just mentioning again that x is a sum of 6 indicators, not 14 indicators here, because just think about how you would write x as a sum of 14 indicators. It would be I1 would have to be 1. It would have to be dependent on what other, so I1, so if you were doing x as I1 to I14, then your indicators would refer to the rolls of the die, and so these rolls are independent of one another, but you would need then so it would have to be like I1 would be that the first roll is one of exactly a pair of that the first what you roll in the first roll appears exactly once again, or something like that. I don't see how you could write it as a sum of 14. So, but writing it as a sum of 6 makes sense. So that's the show for today. I hope you have a great day, and I will see you on Wednesday.